take them downing, take them downing, take them down. As you look, the whole room explodes. Take them downing, take them downing, take them. As you look, the whole room explodes.
Thank you. Thanks for that introduction. So my name's Viegers. I'm from the Netherlands. I work for MongoDB as a senior solutions architect. As was mentioned in the introduction, my background is mostly in fleet management and logistics solutions, tracking large numbers of trucks and trailers around the globe, dealing with engine management data, analyzing that in real time, mostly to improve fuel performance, driver safety, reduce CO2 emissions, that kind of thing. I sold my company 2 years ago to our largest competitor in Europe. Now I work for MongoDB, and I lead a special interest group that focuses on machine-to-machine and Internet of Things solutions. And that's what I'm going to talk to you about today, how MongoDB can be used for Internet of Things applications. And in particular, I'm going to show you a number of the real-life use cases where MongoDB is used at massive scale for these kind of applications. So for those of you who don't know MongoDB, we're a fairly young company. We've been around since 2009. We're about 350 people worldwide. We're headquartered in New York. We have a large large development center in Palo Alto. In Europe, our largest support center is based in Dublin. We have an office in London, which is where I'm employed by. We also have our own people here in Israel. We have an office in Australia, India, and growing very rapidly. We have about 1,000 paying customers. We're an open source product. More than 7 million organizations in the world use our technology. And we're funded by some well-known investors. So as mentioned, we're an open source product. We have 7 million downloads of our product. One of the successful things we've been doing is providing free online education. You can go onto our website and do courses both for DevOps and developers. We're very active in MongoDB user groups. We get together at meetups all over the world and talk about the cool applications based on MongoDB. So MongoDB is a document database. We store our data in what we call a document. And a document, opposite to how you would store things in a relational database, is an associative array, a list of keys and values, where each value itself can be a complex document itself. It can be an array of values. It can be a subdocument. And the most common way of representing a document is in a JSON format, as shown in this example, where in a relational world you would store data over multiple tables, do a join between the data, mostly to optimize the storage. In MongoDB you would not do that. You would just store the document as is and optimize for usage. And the attractive thing of this is that the document represents the entity in your source code a lot closer than a relational model would do. And the other attractive part of it is that you can store multiple documents in what we call a collection. So the equivalent of a table in MongoDB is what we call a collection. And different documents in the same collection do not necessarily need to have the exact same structure. And that's very attractive for when you need to deal with semi-structured data or when there's a new version of your code with a slightly different data model. You don't need to update the existing data structures. You can just start using new structures as long as your application is able to deal with that. But many of the features that you would be used to in a relational world, like having secondary indexes on any of these properties, that's still supported in MongoDB as well. And in particular for Internet of Things and machine-to-machine applications, this flexible document model is very attractive. So if we relate that to my past, for example, where we were storing hundreds of millions of GPS positions each day, doing a query for getting all the GPS positions for a vehicle for a day would mean querying well over 1,000 records. In MongoDB, the way you would model this is that you would have a list of positions and basically have one document per day. And each insert would be an update of an existing document, but retrieving the position history of a vehicle would mean just one route to the database. So another way of representing this is that in a relational world, you would, if you would park your car in a parking lot, you'd really take it apart, put all the parts on the shelf, very efficient for storage. In MongoDB, you would just store the car. Obviously much less efficient for storage, but much more efficient for usage. And that's where, with enabling the way we write modern applications and the way we run modern applications, optimizing for usage with less effort and less cost is what most of us are concerned about these days. MongoDB scales horizontally, and we do that through a concept called sharding. In essence, what you do is that the data set that you have, you partition based on ranges. So let's say that there's a collection with user information. You could partition this on the username, and then MongoDB creates logical ranges of data. We call those chunks. And as soon as those chunks reach a size of 64 megabyte in size or more than 100,000 documents inside one chunk, MongoDB will automatically split that chunk into two chunks, and MongoDB can then freely decide when to move a chunk from one part of your infrastructure, so one shard of your infrastructure, to another shard. And that's how MongoDB will keep the data balanced automatically, and from your application, you don't need to be aware of that. You don't know in the application where exactly your data resides. All your queries go through what's called a query router, and the query router will decide, knowing where the data in the distributed environment resides, where the query will need to be executed. And from the application perspective, again, in theory, you don't need to be aware of this. In practice, the more you know how this works, the better performance you will get out of your system. Because the way the query router works is that if, based on the query router can decide where the data resides in the infrastructure, it can actually target that query to the right shard or shards within your infrastructure and only execute the query there. So in the example that I gave of a user store where you would have partitioned the data based on the username, if you would query for a specific user or a specific range of users, then it's very easy to target that query to just the one shard where the user document resides. But if you would ask, for example, give me all the users that live in Israel, then the query router has no option but to run the query on all the available shards. It has the advantage that those queries will then be executed in parallel and return the data back to the application. It then depends on your query. If you do a sort or a limit, it may need to wait until all the shards have responded before it can hand back the data to the application. Or if that's not the case, as soon as the first shard will respond, the query router will hand the data back to the driver. So horizontal scaling is the way we scale within MongoDB. The other important concept is the concept of replication. Replication is what we use for our high availability and disaster recovery. And the concept consists of what we call replica sets. A replica set consists of an odd number of nodes And there's asynchronous replication between the nodes inside a replica set. One of the nodes is elected a primary, and all write operations are handled by the primary. In MongoDB, there's no option. All write operations will need to go through the primary, and the secondaries will then asynchronously replicate themselves off the primary. If the primary would fail, the secondaries would realize that there's a heartbeat concept going on between these members of the replica set. And as long as they're still part of what we call a majority of the original replica set, then the secondaries will hold an election automatically and appoint one of these secondaries to become the new primary. And your driver will then automatically route the next write operations to this new primary. And this is a fully automated failover. There's a concept in MongoDB that we call write concern, which is where you can decide how certain you want to be that you can never lose any data. For example, the most trivial write concern would be an unacknowledged write, a fire and forget kind of write methodology where your application will just send its writes to the primary, not wait for any acknowledgement. Obviously, it's never your intent to lose data, but if the primary would become unavailable, there is a risk of losing data in that case. So this would be a write concern that you would only use for things like logging applications where write throughput is your main concern, but it's not the end of the world if you would lose a write operation. The default write concern is what we call an acknowledged write. And this is where the primary server will acknowledge in RAM a write operation that it has received before it hands back control to the driver. So if the application cannot reach the primary for whatever reason, the application is blocked until it receives this acknowledgement. Again, this is done purely in RAM. If the server would crash after it sent the acknowledgement, but before the data is flushed to disk, there's still a risk of losing that write operation. If you want to avoid any risk of losing data, there's various alternative options that you have. You can, for example, specify that at least 2 of the members of this replica set must have acknowledged the write. And we call that the W parameter in the write concern. So you could say W equals 2. That means control is only handed back to the application when at least 2 of these members in this replica set have acknowledged the write. Or there's a special value called majority. You don't need to have 3 members. You can have 5 or 7 or up to 12 members in your replica set. As long as a majority would have acknowledged, control is handed back. You can also customize this by saying at least 2 servers in 2 different racks or in 2 different data centers must have acknowledged the write. The last option you have is that you can force a write operation to be written to the journal on the primary, so that you're sure that it has been flushed to disk, so that if a server would fail and it comes back up, then it can check from the journal if all the write operations have been applied to the database. So a typical MongoDB configuration would look something like this, where your application uses a MongoDB driver. We support all popular development environments out there. I think there are 12 or 14 officially MongoDB supported drivers for, as I said, for all popular development environments. And then there are several drivers out there supported by the community as well. And the infrastructure would consist of a number of shards, each shard itself being a standalone replica set. Where again, the replica set is for the high availability, the sharding is for the scaling. So if we move on to the Internet of Things, for those of you who are not aware what the Internet of Things is, it's a computing concept whereby everyday goods are connected to the Internet. Gartner has predicted that by the year 2020, anything that's worth more than $100 will have some sensor of some sort communicating with whatever needs to be interested in information of that object. So our clothes, the chair that you're sitting on, everything will be equipped with sensoring equipment. And those sensors will be connected to the internet and send information generally to a central decision platform where we can count and track everything that's out there. Now, why is this of interest? So first of all, by being able to track and count everything, we know when things need to be replaced. We have a great opportunity to reduce waste and loss and cost. Objects become bigger than they are themselves. They get what we call ambient intelligence. They know about their surroundings, and the whole world that we live in essentially becomes one big computing system. There's a number of steps that we go through in making things smart. So if we take the example of your toaster at home, today the color of your toast is totally determined by the mechanics inside your toaster. And if your wife happened to have toasted just before you, your toast may come out a little bit darker than you were intending. Well, with electrification, you would put a microcontroller in that toaster, and now the microcontroller determines the color of your toast and makes that a whole lot more reliable. So the first step in making things smart is electrification. It's adding microcontrollers to these everyday objects. The second step would be remote communication, is have the object be able to exchange the data that it measures locally to a central decision platform. And that's where in most of the applications that we're doing today would go up to that step. The full Internet of Things applications, in my opinion, is where we go to automated control, where we actually make intelligent decisions based on the information that we've received from the devices around us. And again, if this sounds a bit abstract, I'm going to give a number of real-time use cases today. The other thing that I wanted to point out is that really the Internet of Things is already here today. This is data from Cisco. In the year 2008, there were actually more devices connected to the internet than people. And the prediction is that this will grow tremendously in the years to come. And this, there are different predictions, but they all boil down to pretty much the same thing. The prediction here is that by the year 2020, we'll have about 7.6 billion people connected to the internet, but 50 billion devices, which is the equivalent of approximately 7 devices per person on the internet. And where we've seen a clear evolution of the World Wide Web, and the World Wide Web is often used as equivalent to the internet, but as you all know, the World Wide Web really is the application layer on top of the internet. We've gone from academia to a brochure web to a transactional web. Companies like Amazon were the leaders in that, to the social web that we have today. We haven't really seen this kind of evolution in the internet itself. Sure, we're handling a lot more information on the internet. Things have become more secure, but a true evolution of the internet is just about to happen as we speak. And we're all the lucky ones to live it and to build the applications supporting this. So where the Internet of Things is clearly different than the internet that we've been using so far is that it's much more mobile than fixed. It needs new architecture models, new IP protocol. We've run out of IP addresses, and we certainly cannot support without IPv6 the 50 billion devices connected to the internet. The Internet of Things is very sensor-laden. All of the projects we're doing today is about storing sensor data, or telemetry data, as we call it. And again, many more machines than people. So why is MongoDB a good solution for this kind of application? Or why is NoSQL in general a good solution for this kind of application? Well, first of all, Internet of Things processes are real-time. We need to analyze them in real time. When we're guiding trucks through or buses through London and try avoid heavy traffic, you cannot wait for minutes or even seconds before you decide that the truck actually needs to take a different turn. Being able to analyze large volumes of data in real time is one of the main challenges in Internet of Things applications. In MongoDB, we have a built-in aggregation framework that allows you to analyze data in real time. There's also a MapReduce component, which was the predecessor of the aggregation framework. But today we recommend to use the aggregation framework. And that supports very powerful functionalities such as geoqueries, for example. Next, our lives will depend on the Internet of Things. Our grandmothers will be carrying sensors that tell their doctors what they need to know about their health. We cannot afford these systems to ever go down. Reliability and performance are critical, and this is where NoSQL plays a very important role, because these technologies have been designed to always be available, never go down, not even during maintenance windows. And relational technologies can simply not scale to the level that is required for Internet of Things applications. In the small projects that we're doing today, we're talking often hundreds of thousands of operations per second. Internet of Things data can come in any format, and this is where the flexibility of the document model is very powerful. When you deal with different kinds of sensor data, some of it may be numeric, others may be alphanumeric, you may receive lists of data, pictures, videos, all sorts of different data that somehow you want to treat similar. And this is what a document database is designed to do. Time series, most of the sensor applications that we're doing really are time series applications. With the example I gave for storing data in arrays, it gives you a much higher read throughput in getting your data out. And lastly, also very important, Internet of Things applications will increasingly consume the database as a service. This is one of the areas where we see huge growth in MongoDB as well. And modern applications will much more often consume database as a service. So some of the examples of where we're doing this today. One of the main projects I'm involved with myself at the moment is with Bosch. I'm sure that most of you will know Bosch from the home appliances. Bosch is actually a huge manufacturer of sensor information. One of the factories I'm working with is a factory in Germany, in Reutlingen, where they make so-called MEMS sensors. They build over 600 million of these sensors per day. All your mobile phones will have a Bosch sensor of some sort. All of our cars will have at least 50 Bosch sensors behind the dashboard, even though we may not realize it. And Bosch has very heavily betted on the Internet of Things for their future. They've built a platform on top of MongoDB for building Internet of Things applications. And this is available both through divisions internally within Bosch, as well as they make it commercially available to anyone who's interested in using their platform. And the platform, in essence, encapsulates the magic of storing all of this sensor data at large volumes in a database and retrieving it back. You can access it over a REST layer. And the first project that I was involved with on top of this, this platform is for manufacturing airplanes. And what I didn't realize before going into this project is that the manufacturing of an airplane is very different from manufacturing a car, for example, in that you don't follow a standard assembly line. In this case, the drills that are provided by Bosch for tightening the screws have a little display on them, which tell the mechanic what he needs to do. And as he's executing his task, it tells the mechanic how well he's doing it, and it captures the speed, the torque, the angle at which these screws are being tightened, stores all that information underneath in MongoDB, which then is used for safety purposes later, insurance purposes later on. And that's the, I think the opportunity that we have is that by using these Internet of Things applications, we can actually design new services to the world and to your customers, and find new revenue streams that were simply not there before. The next example is a company called Barco. Barco is a Belgian company. They are one of the world leaders in building display technology, displays, for example, for football stadiums or Trafalgar Square. In this case, we work with their healthcare division, and they make very high quality top-end displays for medical applications like radiology, surgery, all the way to bedside entertainment systems. And in particular, these high-end devices, a hospital will have maybe 2 or 3 of them. With this application, they would track in hospitals worldwide where these devices are, how they're being used, what the diagnostics of these devices are they still giving the correct quality. There are different regulatory requirements in different countries. And all of this is automated centrally by having these devices exchange their information. It's quite a complex architecture that they've built on top of Node.js and MongoDB. Today, we're tracking about 65,000 of these devices worldwide. It's been very successful. And it will be rolled out to the middle end and the lower end devices, also the bedside entertainment system. And we're expecting the number of devices tracked by Barco to grow to about 1.5 million in the next 4 years. The last example is a company called Masternode. They're very similar to the work that I've done personally in the past. They're a UK and France-based company tracking vehicles, mostly service vehicles, doing dispatch information with the drivers on the kind of operations they need to do. And in real time, they track the engine management system. So they measure how often the driver applies the brake, how harsh he applies the brakes, whether he uses his cruise control when he shifts gear, that kind of information. And they analyze that information in real time to give feedback back to the driver, how he needs to change his driving style, mostly to improve his fuel consumption, and as a result also have lower CO2 emissions. They would handle about 150,000 of these messages per minute. So not huge, but still quite a data-intensive application. And they need to store that information for 7 years for regulatory purposes. So they've used quite an innovative way of using our sharding principle in having the real-time data available on different shards than the historic data. So if we summarize what I've spoken about, I think an important thing to realize is that the database world of the future, especially the big data database world, is very polyglot. There is not one solution that fits all of the use cases. And it's important to choose the use case that best fits your, the technology that best fits your use case. Our vision in MongoDB is that we try and be as general purpose as possible. We're certainly not the best at everything, but we're good enough at many things, and we strive to have a very functionally rich database. If you would map database functionality against scalability and performance, then in today's environment, the relational databases clearly have the most functionality, but they also have the poorest scalability. And what you often see, it's a trade-off between functionality and scalability. If you look at the other end at key value stores, they have huge performance, but lack functionality. And MongoDB tries to position itself just where the line goes on the edge of still offering you very rich functionality. So we do have secondary indexes, we do have built-in aggregation, we do have geospatial indexes, but not compromise on the scalability and performance aspects. We're still in the early days of where we are with the technology on big data. Things I'm sure will improve going forward. There's a huge number of different NoSQL technologies available today. Without question, there'll be some consolidation there as well. But the recommendation that I have, and I know that that the other NoSQL vendors do that as well, is before you start with any of the NoSQL technologies, first of all, speak to us and make sure that we help you identify that your use case is actually a good fit to the technologies that we offer. And use the gain in productivity that you get from using the NoSQL technologies and actually trying out different ways of resolving the same solution. In particular in MongoDB, the way you do your schema design has a huge impact on the ultimate performance you get out of the solution. And the flexibility you have in the schema means that often you can solve the same problem in many different ways, with huge impact on the kind of performance that you'd get ultimately. And again, the main rule of thumb there is that in the schema design, it's important to ask yourself up front, what's the kind of question that you're going to ask from the database, and model to optimize for usage. So my last slide is that we strive to fit very well in agile development environments. The fact that you don't need to do any database updates when you change your database schema, for example, means that rolling out new versions of your applications go a lot more smooth than you were used to. And of course, grow with the success of your application and be highly scalable at it. So thank you very much for your attention.
Thanks a lot. I think we have time for a couple questions. Anyone? Come on, guys. Otherwise, no break. Nope.
No? Okay, well, thank you. I'm here all of today, so if any questions come up, feel free and come and talk to me or any of my colleagues out here. Again, thank you very much.
Thanks a lot.